So this question is going to apply Bayes' theorem, but it's going to be multiple steps before we actually come to the Bayes' theorem. So first pause the video and read the question carefully. Now the first thing is to look at the data that are given. Let's look at this. What this really means is that the test for HIV was done on a big sample of people. Maybe some of them were known to have the HIV virus or antibodies present. So, and the other group was free of HIV, so that was known, and this test was administered to see if it actually works. So the first row is looking at the group of people who probably had the antibodies of the virus. Out of the people who actually had the antibodies, 0.9985 was the probability that they tested positive, and it's obviously high because the test is pretty good. And out of the people who had the antibodies present, the test was wrong with a probability of 0.0015, which means for a population that was known to have, so this is knowing that they had, let's call it disease, just for being brief, and just easier to write it down as one letter. So knowing that, or given that they had the disease, 0.9985 tested positive and 0.0015 was the probability that they tested negative. So writing this down, this is what it would look like. So knowing that someone has the disease, the probability that they tested positive is 0.9985. Knowing that they had the disease, or the antibodies were present, the probability that the test showed negative was 0.0015. Now the second row is for people who are known to not have the antibodies, so let's just call it no disease. A small percent of them still tested positive, so there was a small probability that they would test positive even if we knew that they did not have the disease. So knowing that, let's write this down here, knowing that the person did not have the disease, the probability that he or she tested positive was 0.0060, a small chance. Now the second number, again, it belongs to the group that we know does not have the disease. So given that they do not have the disease, 0.9940 was the probability that they tested negative, which was a correct result. Now there's always one more piece of information given, and this is through various collection of data. 1% of the population actually has the disease. Okay, that is how rare the disease is. The chance that someone has the disease is 1%. 1% is 1 divided by 100, and that's where the 0.01 comes from. And the immediate consequence of that is, what's the opposite? Probability that someone does not have the disease is 1 minus 0.01, which is 0.99. So let's draw the Venn diagram. The tree diagram for this particular problem, not the Venn diagram. So we start off with a general person from the population. It's possible that they have the disease or they do not have the disease. So disease, no disease. There are only two possibilities with a probability of 0.01. The person has the disease. With a probability of 0.99, the person does not have the disease. Now, once we know that the person has the disease, so at this point we know the person has the disease, and if they take the test, what is the probability that they'll test positive and what's the probability that they'll test negative. So a person who has the disease takes the test. It's possible that they'll test positive and it's also possible that they'll test negative because the test is not 100% correct. So at this point we know that someone has the disease. So knowing that someone has the disease, what is the probability that they'll test positive? It's 0.9985. At this point we know the person has the disease. What is the probability that they'll test negative? So there would be negative given disease, so that's 0.0015. Now let's look at the other side, which is a person does not have the disease and the test is administered on them. Even if they do not have the disease, it is still possible that the test will show positive, and it's also possible, obviously, that it will show negative. So at this point we know that the person does not have the disease. So knowing that the person does not have the disease, there is a small chance, 0.0060 chance, that the person will still show positive. And of course there is a large probability, since the test is pretty good, that the person will, without the disease, takes the test and will show negative. So this is a tree diagram. So how do we use this tree diagram? If I want to know what the probability that someone has the disease and tests positive is, so the word and is different from given that. So we start here. So first the probability that they have the disease, 0.01, and knowing that they have the disease, what is the probability that they'll test positive? So we multiply that with 0.9985. What if we need to figure out the probability that the person does not have the disease and tests negative? So the word here is and, not given that. So we don't know what the probability of both happening is. So we start off with what's the probability that someone has the disease, so that's 0.99, times what is the probability that they will show negative, so that's this branch, so that's 0.9940. We multiply the two and that gives us the probability of no disease and showing negative. So the one thing that we have to remember is this: probability that someone does not have the disease and shows negative is not the same as probability that someone shows negative given that they have no disease. So given that is different from and. Now the first question is, what is the probability that a random person takes the test and the test shows positive? So basically we're trying to figure out the probability that the test will show positive, and this is what we're trying to figure out. So we have to think about how to do the calculation. So when does someone show positive? When they have the disease and they show positive, or they do not have the disease and they show positive. Now from this point on, so the word or translates to addition. We can use the formula, which is conditional. Probability of D and positive is probability of D times probability of positive, given that the person has the disease, because being positive and having disease are not independent of each other, because showing positive does depend on whether the person has the disease or not. So these are not independent. So that's why we're using the conditional probability formula here. Now similarly, probability of no disease and positive is probability of no disease times probability of positive under the condition that the person does not have the disease. And then of course we just plug in the numbers that we've already written down here in the previous slide, and then we get a probability which is 0.0159. We change it to a percent, it's 1.59%. That 1.59% chance that a person tests positive. Note that this sounds reasonable because 1% of the population actually has the disease. And there may be some false positives, so including the false positives, 1.59% of the people will show a positive test result. Now, another way to do the calculation is by using the conditional probability tree diagram. So probability of a person showing positive can happen in two cases. One is they have the disease and they show positive, they do not have the disease and show positive. The word or goes with addition. What's the probability that a person has the disease, so D, and positive? So let's look at the the tree diagram. So person shows the disease and person has the disease and the test shows a positive result. So we have to go down this path. So probability of disease is 0.01 times the probability that they show positive given that they already have the disease is 0.9985. So multiply those two probabilities. The next probability we have to figure out is probability that someone does not have the disease and still shows positive. So we have to go down a different path now. We start off at the starting point again. The person does not have the disease with a probability of 0.99 and shows positive, so that's a probability of 0.0060. So multiplying the probabilities on the green path, we get 0.99 times 0.0060. So sometimes using the tree diagram is much easier than breaking down the formulas. So from this point on, you can just use the tree diagram and come up with the final probability by using your calculator and adding the two individual probabilities, and we get the same answer, which is 1.59. Now there are certain terms that are used related to these tests. Sensitivity of a test, so that's a measurement of how good the test is. So it is the probability that the test shows positive. So let's write this down. It's the probability that the test shows positive knowing that someone has the disease. So if someone has the disease, what is the probability that the test will show positive? This better be a number that is pretty high for a test to be useful. So that would be, in this case, I think 0.9985. The next is specificity. What is the probability? So what is the specificity? It is the probability that the test shows negative knowing that the person does not have the disease. And this number also is usually pretty high for the test to be good. And finally, the positive predictive value. The probability that someone has the disease once you know that the test has shown positive. Because the test can show positive and there is a small chance that a person does not have the disease no matter how great the test is. And that positive predictive value is the probability that someone actually has the disease once we know that the test has shown positive. So finally, we've come to a point where we calculate the positive predictive value, which means what is the probability that a person has the disease given that the test has shown positive. Note that there is still a chance that the person does not have the disease even if the test has shown positive. So probability that someone has the disease given that the test shows positive is a conditional, which is probability of both divided by the probability of the second, which is probability of positive. So what is the probability that someone has the disease and tests positive? So that would be probability that someone has the disease times times 0.9985, which is the probability that the test shows positive given that someone has the disease. So you can either use the formula, which is the multiplication rule, or you can use the tree diagram to come up with the numerator. And the denominator is probability of positive that we calculated from the previous part. So this would be probability of disease times probability of positive given disease divided by probability of positive. If you remember, we got that by saying there are two cases. The test could show positive when you have the disease and positive when you do not have the disease, which means probability of positive, probability of disease and positive, or so that is plus probability of no disease and still shows positive. If you remember, that's how we got the denominator, which is probability of positive. And for each of these we can use the tree diagram to come up with the probabilities and then use the calculator. So this is really what Bayes' theorem is. Using the Bayes' theorem directly can be a little confusing, but if you break it down into smaller steps, it's just easier to apply the formulas and finally get the answer. If you're given some data related to a test, then usually these two are given to us. What's the probability that someone shows positive given that they actually have the disease? It's a number that's pretty high, 0.9985. This is also usually given to us when we use the Bayes' theorem. What is the probability that someone shows negative given that they do not have the disease? That's pretty high, 0.9940. And positive predictive value, notice this number. No matter how great the test is, look at the positive predictive value. Knowing that you've shown positive on a test, look at the probability that you actually have the disease. It's about 62%, which means there is still a chance, about 37% chance that you do not have the disease. So that would be the positive predictive value that we got from the last part. So the Bayes theorem applied to this specific problem looks like this. You can do it in small steps, starting off with probability of D and positive divided by probability of positive. Slowly break it down to probability of D times probability of positive given D, and then you can break down the probability of positive as probability of, maybe first go here, disease and positive, or, which is plus, probability of no disease and positive, and then finally from here to here, which is probability of disease times probability of positive given disease divided by breaking each using the multiplication rule for events that are not independent, probability of D and, which is times probability of positive given that D happened, or, so that's plus probability of no disease times probability of positive given no disease.